They led life's earthly parade for more than 160 million years. They conquered the land, and now they capture our imagination. Before they became extinct, they matched function with form to perfection in this magnificent beast. They were dinosaurs. This is Tyrannosaurus Rex, king of the beasts. Big Sky Country, New Mexico, 1993. Peace might be at hand in the Middle East, but the big news here was the discovery of the world's first known Tyrannosaurus footprint. 65 million years ago, a large tyrannosaur stepped in mud. The footprint filled with sand, which hardened to form a sandstone plaster cast. 65 million years later, the University of Colorado's Martin Lockley found it, poised to strike and as fresh as yesterday, sculpted on this rock.
That's really something. It's a big animal. Well, that would make sense because Tyrannosaurus
Dr. Lockley.
is so darn big. This is a Tyrannosaurus Rex footprint. Tyrannosaurus footprint. We're sure about that now for a number of reasons. One is it's definitely made by a carnivorous dinosaur. It has digit 1, a hallux, and it has claw impressions. That's typical of a theropod or a carnivore.
85 centimeters long. Each claw-tipped foot covered an area almost the size of an open umbrella. But then it had to support and propel up to 6 metric tons of muscle and bone. The dinosaur's final flowering produced Tyrannosaurus. In geological terms, T-Rex found life just before the dinosaurs' mass extinction. From tail tip to snout, a 6-ton adult extended 12 meters, over 2 car lengths. Seldom has nature crafted such a perfect killing machine. Perfection took time. Early dinosaurs, Eoraptor and Coelophysis, appeared 225 million years ago. The huge primordial continent was starting to break up. From Triassic times to the Jurassic period, to Stegosaurus, Diplodocus, and other plant eaters, including a giant from China, Memachisaurus. By Cretaceous times, continents had taken on familiar shapes. Dinosaurs, including Parasaurolophus and Triceratops, were trying on different shapes too. By 70 million years ago, what looks like our modern world map is populated by species in the Tyrannosaur group, Albertosaurus, Nanotyrannus, and Tarbosaurus among them. What sort of world might it have been? Tyrannosaurs chase. Corythosaurs flee. How does it end? We'll find out. But first, what made this killer tick? In all, some 50 fang-like teeth projected from a powerfully muscled jaw. This leg bone from a plant-eating hadrosaur was snapped by a tyrannosaur. Embedded deep in the hadrosaur bone, a broken tyrannosaur tooth. Other victims included the massive rhinoceros-like Triceratops.
There are many, many little puncture wounds that we believe are bite marks from a Tyrannosaurus rex. You can see there are almost...
For Peter Larson, this Triceratops bone is a powerful indication of a Tyrannosaur's strength.
And if we take two teeth from a Tyrannosaurus, you can see that they nicely fit into these holes.
What about the teeth?
The teeth of Tyrannosaurus rex are very formidable weapons. In fact, this bone, as you've seen, has many, many bite marks on it. But this one particular hole on this end tells us quite a story. If we take this tooth and insert it, it actually goes clear through the hole in the femur. We believe that this femur, when it was attached to the Triceratops, which is attached right here, we believe that it was grabbed onto by the Tyrannosaurus rex, and this bone was just ripped off of the body of the Triceratops.
The Badlands of Alberta, so called because aeons of erosion left the land gullied and broken. The Badlands is dinosaur country, rich in fossil remains, which is why the Royal Tyrrell Museum of Paleontology is located here.
I think the worst part is going to be trying to get the hip section back together. It looks pretty crumbly.
Dr. Philip Curry, head of dinosaur research, is a specialist on carnivores.
Where's the rest of it right now? In that block, or?
The Royal Tyrrell Museum boasts the world's largest exhibit, with 40 dinosaur species restored, many from the Badlands. Not content with rebuilding their bones, Dr. Curry applies scientific analysis to the question, how did they live?
Tyrannosaur teeth, like all carnivore teeth, are very long and tapering. And we think that this is a very simple structure when you look at it at first. But in fact, as you start looking closer, you'll see that there are in fact serrations running down the back of the tooth and the front of the tooth. And each one of those serrations is like a little tooth of its own. So that when a tyrannosaur is biting into another animal and its tooth goes across like that, across the flesh, what each one of those serrations is doing is hooking the meat. And as the meat gets hooked, it gets pulled between the serrations and cut. And so that when a tyrannosaur bites into another animal, its teeth bite very efficiently into the flesh, and they cut the meat and they cut the bone too. So that's one characteristic that's quite different than what we would think.
Serrations, front and back, made each edge a sawtooth. Imagine a mouthful of 50 serrated steak knives ripping flesh. The result, even on big Triceratops bones, was devastating. One disadvantage, serrations create weak spots, leaving material liable to snap. Curiously, these serrations do not stem from a simple slit. Instead, their bases form rounded pinholes. At Keio University's Science and Engineering Department, an experiment by Professor Nobutoshi Yamasaki explains the role of these pinholes. Serrations in the simulated tooth on the right consist of simple slits. On the left, pinhole slits, as in real teeth. A hydraulic ram tugs both teeth with equal force. Suddenly, the one with a straight slit broke, says Yamasaki, because forces focus on the inner end, making it weak. Pinhole slits, like those in real teeth, spread the force. Engineers understand the pinhole principle very well, as it affects teeth in steel and ceramic blades. The mystery is, how did T-Rex devise the pinhole principle 70 million years ago without the benefit of human engineering? For scientists like Phil Currie, their hunt for the dragon is an ongoing quest to reveal nature's perfections. Hill City, South Dakota. Old-time prospectors might have said, "There's bones in them thar hills." The bones come here, to the Black Hills Institute of Geological Research, and to the knowledgeable eye of its director, Peter Larson.
This is a rib from the Tyrannosaurus rex known as Stan. If we look closely at this rib, we'll see on the very edge of it a mark. This mark is a healed injury caused by the bite of a Tyrannosaurus rex. This shows us that Tyrannosaurus rex fought among themselves. I believe that Tyrannosaurus was a territorial animal, and when families who lived in certain territories would meet, they would fight for this territory in order to have a place to hunt.
Well-engineered teeth fit in a well-engineered skull. Curiously, the skull was not massive. Rather, massive muscles hung on a lattice of bone. This might have led to severe fractures, except that flexible joints linked the bones. Woodpeckers offer a parallel. One might expect skull damage in a bird which spends life hammering wood with its head. Not so. Joints in its skull act as shock absorbers. Impact stresses never reach the brain. Similar skull joints protected T. rex. Dr. Currie.
Tyrannosaurus, of course, has a very massive skull, but there's a lot of big open areas inside this, and we find that between the bones are actually very loosely attached to each other, so there's movement possible between them. And this is especially obvious at the back of the jaw, where the back of the jaw can actually open up. And when you look at the lower jaw, you can actually see that there's a joint running down the middle of the lower jaw. Now, what these joints are for is to act as shock absorbers. So when Tyrannosaurus is closing his mouth on something, he has less chance that he's going to break his teeth, number one. It allows him to put a lot more power and force on the things that he's eating. And then finally, if the prey is still alive and struggling in his mouth, there's some give inside the jaws, so that again, things don't get broken in the Tyrannosaurus head.
Imagine this. A 6-ton tyrannosaur locks onto an animal with the bulk of, say, a modern rhinoceros. Both bodies twist and turn, but Tyrannosaur's teeth are deep in the flesh of its prey. So its head has to absorb the combined shocks from both animals. Hence its skull joints, massive muscles in place of heavy bone, and the strong, flexible lattice of bone itself. As well as strength, a killer needs finely honed senses to track prey.
I wanted to do that. And then I'll go.
The Foothills Hospital, Calgary.
This is the center, I guess.
Dr. Currie's Albertosaurus skull is here to get a CAT scan. Albertosaurus is a member of the Tyrannosaur group.
Okay, to about here, or should I go all the way through this?
Go back another 1 or 2, might as well.
This way?
Yeah.
Okay.
A series of electronic slices reveal shapes of internal cavities and the organs they housed, including the brain. Much of this brain processed sensory inputs. The lobe on the right, the front, is linked to the sense of smell. The red lobe in the middle to sight. one in the rear, to hearing. T-Rex had little use for intelligence as we know it. Instead, it was acutely aware of its world, reacting rapidly to it. Take the sense of smell, as found in the species Nanotyrannus. This long, rolled turbinate bone in the nasal passage shows that Nanotyrannus had a superb sense of smell. Modern mammals with keen smell often have a large turbinate bone. For example, wild boars scent potatoes and other tubers deep underground. The more convoluted the bone, the more scent organs come into play. To sniff the wind, if you happen to be a boar, a hyena, or Nanotyrannus. Nanotyrannus is the only known dinosaur with such a bone. Ahead of its time, perhaps, it was well equipped to pluck faint odors from passing air. Sight, smell, and hearing. Tyrannosaurus was a radar trap for anything that moved. Behind the ear slits, CAT scan slices reveal keen hearing. Its brain was crammed into a tiny cavity, while large empty sacs took valuable space behind the ears. These were resonators for amplifying sounds. Phil Curry.
Like other dinosaurs, in fact all other animals, there's a big air sac associated with the middle ear in Tyrannosaurus. But what Tyrannosaurs have done is they've taken that air sac and extended it into all the bones around the brain case. And this gives it a much larger size. This means that Tyrannosaurs could increase the frequency of the sounds that they actually heard, and they could hear lower sounds much better. And we know from looking at the nasal structure in duck-billed dinosaurs or hadrosaurs that they probably made very low bellowing sounds. And we think that in Tyrannosaurs, they've extended their ear that way so that they could hear the duck-billed dinosaurs. And if they could hear the duck-billed dinosaurs, they could locate them and then hunt them.
The world of T-Rex was probably dominated by an insect cacophony. So large animals communicated on low frequencies. This explains hollow crests, actually resonator cavities, on skulls of hadrosaurs, such as Parasaurolophus. Tyrannosaurs could intercept low frequencies, locate, home in, and kill. The first mounted skeleton showed T-Rex propped on its tail. First discovered in the year 1900, Pittsburgh's Carnegie Museum of Natural History houses this early display. For decades, paleontologists assumed this model for T-Rex, a slow-moving beast propping itself on its tail like a tripod, or a kangaroo at rest. Not anymore. This fleet-footed runner is Tyrannosaurus rex Mark II. T-Rex Mark II is poised for action, perfectly balanced, fulcrum in its hips. Without wasting energy, this posture supports more than 6 tons at a running speed of 20 kilometers an hour, that of a marathon runner. Its revised posture may help resolve a long-standing mystery, that of the animal's curiously stunted forearms. In 1990, a complete front limb was discovered and displayed at the Museum of the Rockies in Montana. Its finder, Dr. John Horner.
What we've discovered was that, first of all, Tyrannosaurus rex, its arm that you see here, is the same length as mine, has the same length arm. But when we look at the muscle scars and figure out where the muscles would go, we know that only this much of the arm actually stuck out of the body. The rest of it was packed in muscle. Tyrannosaurus rex could lift 400 pounds with one arm, but we know that there was very little rotation, and Tyrannosaurus rex could only move its elbow 3 inches.
It's a matter of balance. With a 12-meter body balanced at the hips, well-developed forearms would have made T-Rex front-heavy. Phil Curry.
The arms of Tyrannosaurus are short compared to its body length, but really they're not that weak. They are quite powerful still, much more powerful than the arms of a human being. The reason the arms became so short is simply because Tyrannosaurus rex was like a teeter-totter. As his skull got bigger, he had to reduce weight in places where he didn't need it.
Tyrannosaurus' physique didn't just happen. 140 million years earlier, the carnivore Coelophysis had well-developed forelimbs. It also had a slender head, preventing it being front-heavy. By Jurassic times, Allosaurus had shifted weight forward into a massive head, better equipped for killing large prey. To preserve its center of balance, forelimbs shrank. By the end of the dinosaur's time on Earth, Tyrannosaurus had become the supreme example of its type. The trend is clear. During the aeon separating Coelophysis at the top from T-Rex, muscle mass moved to the head. To preserve balance, front limbs had to go. Professor Yamasaki studies animal dynamics. His little model shows the absurdity of a three-point stance. T-Rex would be forced to take tiny steps. Not only that, this posture wastes energy in other parts of the body. The wagging tail, for example. By comparison, a two-legged stance propels T-Rex with long, rapid strides. No wasted energy here. Walking speed, 6 kilometers an hour, half again as fast as humans. From the last carnivorous dinosaur to the first, Dr. Paul Sereno made headlines in 1991. The University of Chicago scientists found bones from this earliest known carnivore in Argentina. He named it Eoraptor, the dawn carnivore, the first.
With Eoraptor, we obviously have a very small dinosaur. It's only 1 meter long. This drawing here is actual size. It's a very small dinosaur, but we think that it is an adult.
Eoraptor lived in late Triassic times, a full 160 million years before Tyrannosaurus. A fast bipedal runner with a carnivore's teeth, Eoraptor was little bigger than a goose. Nature repeated herself with Tyrannosaurus, massively scaled up. China. We go back in time. Named for Memenchi in Sichuan province, this is among the strangest beasts in the cabinet of creation. Its 13-meter neck surpasses that of any known animal, including other giant sauropod dinosaurs. "150 million years ago, species such as Diplodocus and Camarasaurus attained giant size. Late Jurassic times brought the longest period of stable climate in Earth's history. Prolonged stability nurtured many huge plant-eating sauropods, Brachiosaurus, for example, and Apatosaurus. Long-necked sauropods have modern counterparts. Giraffes pluck leaves from tall trees, without competition. But Memenchosaurus, grazing on leaves 150 million years ago, was unlike any known sauropod. Its 13-meter neck made it very, very different. First hints of the animal came in the 1950s. In 1987, the Canadian Museum of Nature's Dr. Dale Russell was associated with the discovery of a giant, nearly complete neck.
I realized it was a very strange dinosaur because the neck was longer than the body and the tail combined. So it was difficult to believe that it all belonged in one skeleton, but it had been found in central China in the province of Sichuan, complete in our articulation. So we knew the specimen was complete. I had never seen a dinosaur that strange in my life, and I marveled that a creature that peculiar had ever been found.
Russell is a principal scientist in the Dinosaur Project, an ongoing Chinese and Canadian venture which has unearthed wonders in both countries. But Memenchosaurus is among the most magnificent, the strangest of all.
There are many different kinds of long-necked dinosaurs, and many scientists feel that the primary use of the neck in these animals was so that they could raise the head up high into the branches of trees and be able to browse in leaves. I think that there are some dinosaurs that clearly could eat that way, but I disagree that that model would apply in this case. It is apparent from looking at the detailed structure of the neck that the most natural pose for the neck was nearly horizontally across the ground in front of the animal.
So Memenchosaurus's massive body anchored a 13-meter neck, projecting more or less parallel to the ground. Its neck vertebrae show how Memenchosaurus differed from other long-necked dinosaurs. Long, bony neck ribs projected back from each vertebra, overlapping to support the neck as a whole. Whatever conditions directed this animal's evolution, the result was an extraordinary neck, reinforced from head to shoulders by overlapping, muscle-wrapped neck ribs. Jurassic reinforcing rod. The Chinese Institute of Vertebrate Paleontology in Beijing houses an extraordinary find. A single neck rib, excavated from the Gobi Desert in 1987, measures over 4 meters, longer than a standard car. Imagine the neck, an estimated 13 meters long. Stiffening made the neck less flexible. Mamenchisaurus could move it up or to the side, though just 30 degrees. It could never lift it vertically into trees. Nature's elaborate structure restricted her creature's movement. Dale Russell asks,
why was the neck so long? What did the animal use it for? And one way, which is very obvious, is it was a labor-saving device. Without moving its enormous elephantine body, it could swing a very light neck over a broad arc and eat food from a very broad range of grazing material.
how to support such a neck. Working with Diplodocus tracks near Colorado's Purgatoire River. Dr. Martin Lockley.
We know from the skeletons that the animals had a long tail, but they must have held it up because there's no sign of a tail drag going along here, so they held it up off the ground. I think it must have been a counterbalance to some extent for the long, they had long necks, and they had long tails. And the rest of the body in the middle is central and symmetrical. So it's kind of like I said, it's a counterbalance. Some people have compared it with the architectural construction of a bridge, like a suspension bridge.
Suspension bridges of sinew and bone, 150 million years old. The bridge model fits most sauropods, such as Diplodocus. The bridge's strength depends on the strength of its cables. And it was precisely that, a cable, which helped many sauropod dinosaurs hold their ends up. Hips of a Diplodocus are equivalent to suspension bridge towers. Its cable, a massive sinew running the length of the back, was housed in a groove on top of the vertebrae. Function determines form. This model holds for most sauropods, but what if one evolved separately on an isolated continent, China, in Jurassic times? For Mamenchisaurus, the suspension bridge model doesn't hold. So how did Mamenchisaurus support its neck? To solve this structural design problem, Yamasaki consults bridge construction company engineer Takashi Yasumoto. To fit Mamenchisaurus, the bridge model must be skewed. Sinew supported 1/3 of its neck. But there were no massive sinews running forward. This is where the long neck ribs come in. Meter for meter, muscle-bound neck ribs may have made its neck lighter than other sauropods. Other species had cable-like sinews, says Yamasaki. Mamenchisaurus evolved neck ribs instead. Here's how it worked. When this bamboo blind falls open, we get a long, light rod which you can easily support from one end. Mamenchisaur necks must have been something like this. The model resembles strong, light, split-cane fishing rods. The Science and Engineering Museum, Chengdu, home to Mamenchisaurus. and to Professor Dong Jiming, China's foremost dinosaur hunter. Excavated in 1957, this fossil brought Mamenchisaurus to world attention. Of 6 known individuals, this is the most complete. Just one vital thing was missing. Professor Dong holds the world record for finding new dinosaur species, but he has a confession. When we found this Mamenchisaurus, Dong says, the skull was missing. This is a reproduction, a Diplodocus head. We know this one's wrong. We're going to correct it. North China's Gobi Desert, a forbidding wasteland, and a treasure trove for Jurassic fossils. Chinese and Canadian scientists have been digging here since 1986. The Joint Dinosaur Project was an outstanding success. Never had there been such a sustained search for remains. Among those treasures, a precious, elusive Mamenchisaur jaw. The lower jaw held 16 teeth, teeth which convinced scientists that Mamenchisaurus was indeed different. The evidence was conclusive. Mamenchisaurus was not directly related to Diplodocus and its kin. Teeth are important in classifying dinosaurs. Diplodocus had peg-like ones. But Mamenchisaurus's resembled spoons. Ironically, filling in missing information made the animal even stranger. On top of this dinosaur quarry, the Zhigong Dinosaur Museum in Sichuan. Mamenchisaur teeth occluded badly, says museum director Hui Yuyang. It used its teeth like scissors to cut leaves. The Zhigong Museum collection gives clues about the shape of Mamenchisaur's skull, its jaw movements, the position of eyes, nostrils, and so on. This information lets the past take shape in a computer. Like T-Rex, a Mamenchisaurus skull combined hollow spaces with bone to reduce weight. Now, to flesh out the bones, the apertures in front of the eyes are nostrils. Mamenchisaurus could not grind leaves with a simple jaw which moved only up and down. The shape of its teeth confirms that. A long extinct plant, Benetites, was a staple in sauropod diets. In Jurassic times, Benetites grew in conditions not unlike the modern Gobi Desert, hot and dry. It grew about 3 meters high, just right for Mamenchisaur heads. A picture starts to come together of an animal so massive that it had to swing a long neck rather than shift a huge body. Plant fiber is hard to digest. To grind it down, modern mammals chew leaves over and over with molar teeth, which Mamenchisaurus didn't have. These teeth only cut. After that, the animal pushed unchewed leaves down its throat with its tongue. That explains why sauropods ingested stones to grind plant fibers for them. At Brigham Young University, Dr. Wade Miller.
So these gastroliths or stomach stones are used in a grinding motion as these things continually move around by muscle contractions and enable the sauropod dinosaurs to grind their food to macerate the cellulose material of the plants in order to gain the food value that they need from the plants that they're eating.
Some birds, which have no teeth, still do the same, swallowing stomach stones deliberately to grind tough fiber for them. Fiber wears down. So do stones. Gastroliths found with sauropod bones are usually smooth and rounded. Dr. Miller.
Even before that, once the gastroliths grind the food down to a certain size, the bacteria within the animal that must have existed would also be a help that was necessary in gaining the food value the dinosaur needed. And so bacterial colonies within the digestive system would also help by fermentation and producing the necessary food value for the dinosaur.
Microbes help break down food in animals' guts. In plant-eating dinosaurs, they were crucial. An elegant experiment at Cochin University shows why sauropod dinosaurs became so large. For 2 months, these tadpoles ate spinach. This group ate only worms. Plant-fed tadpoles, like the one on top, grew twice as large as protein eaters. Plant eaters needed more microbes, and hence longer guts, to process plant fiber. Which takes us back from tiny tadpoles to the 25-ton monster, Mamenchisaurus. The belly of this beast, the length of its gut anyway, may have been 10 times that of the animal itself, full of microbes fermenting plant leaves, generating heat.
And on this rib you can see 1, 2, 3 excavations that pass well into the interior of the rib.
At the Museum of Western Colorado, Dr. Brooks Britt studies sauropod cooling systems. These Apatosaurus bones are full of natural cavities. With virtual compost heaps generating heat in their guts, sauropods, it seems, were air-cooled.
It's important to remember here that even though we're showing a lot of separate balloons to represent air sacs, all these were interconnected. There was a big tube running down through here that was thicker than my arm, and it came down and went into here, and went into here, and then this flowed up along the side of the vertebra, up into all these different areas.
So, what have we got? 25-ton adult Mamenchisauruses, fueled by inefficient, microbe-fired plant fiber, fermenting in huge air-cooled guts. What sort of lung sustained this beast? At Purdue University, Dr. Richard Hengst, with artificial neck and oil drum lungs, is trying to find out.
6.25.
Hard work, but air had to pass in and out along a 13-meter neck. 9 drums hold 1,900 liters of air.
In using what we've seen here, we find that about 800 liters per minute is about what Mamenchisaurus could get to its lungs. And that isn't a lot of oxygen. And therefore, even at a low metabolic rate, Mamenchisaurus breathing through its nose could probably only move very, very slowly. So it would have to open its mouth. And even then it's going to be difficult to breathe rapidly enough to get it up just even the mildest hill or perhaps fight off a predator.
175.
We don't know how they fought predators, but we do know how sauropods moved.
Yeah, 156. I think the main thing that it shows is that you have a
Dr. Martin
you
Lockley.
have a very narrow trackway, because you can put a line right down the middle here, and you can see that the back footprints, like here and there, they touch on this midline. So this means that the animal was very upright and erect, and almost put one foot in front of another as it walked along.
Dr. Lockley, studying Diplodocus tracks, suggests that many sauropods walked like large mammals, advancing 2 legs at a time. If that were true of Mamenchisaurus, it would walk twice as fast as humans. That sort of speed seemed unlikely to Keio University's Professor Yamasaki. If a 25-ton body moved 2 quite small feet at a time, like this, says Yamasaki, the other 2 would sink into the ground. No, this animal moved just 1 foot at a time, keeping the other 3 firmly planted. For example, it moved 1 front leg while the other 3 took the weight, then a hind leg, and so on. That gives a walking speed less than 3 kilometers an hour, much less than humans. Incredibly, this creature lived. Its evolution nurtured through millions of years by a stable Jurassic climate. Its gestation took time. 225 million years ago, this was our world. Small, fast, bipedal carnivores sprang from those late Triassic times. This is the goose-sized Eoraptor. From this to Mamenchisaurus would take more than 60 million years. Housed in Beijing is what we might call a halfway species, also from the Gobi, the ancient sauropod Lufengosaurus. Its bones suggest that Lufengosaurus stood up on 2 legs, but that it walked on 4. As the nursery rhyme goes, he was neither up nor down. And the teeth? They have become the peg-like teeth of herbivores. Why did small bipedal carnivores like Eoraptor evolve into herbivores such as the ancient sauropod Lufengosaurus? That mystery has yet to be solved. And surely factors other than stable climate gave us giant sauropods. Evolving in the geological isolation of Jurassic China, Mamenchisaurus was exceptional in many ways. Dr. Russell.
The reason why they probably increased in girth was because they were eating very low quality vegetation and they needed the assistance of bacteria to help them digest their food. But this was a slow process. So the animals' bodies, their stomachs grew to very massive size. Their weight grew so that they weighed as much as several elephants all rolled into one, and they simply could not support this gigantic body weight on hind limbs alone. So these were among the first dinosaurs to become truly quadrupedal.
So there we have it. Dinosaurs came and went for 160 million years, both small and great. Meanwhile, drifting continents meant that some of them evolved in isolation. Like Mamenchisaurus and other wonders in what is now the Gobi Desert, for example. The Gobi guards its secrets. Yes, Mamenchi, they're your secrets to know, ours to discover. Did you really evolve that neck to avoid moving your body? At a time when the atmosphere contained less oxygen, is it true you just took half a breath each minute? Perhaps, like modern Nile crocodiles, you had better hemoglobin in your veins than humans. One day, Mamenchi, we'll find out.